Okay, let's cut through the noise for a second. We spend so much time analyzing these big models, LLMs, diffusion models,
Right.
and they're basically, I mean, they're incredible at faking it. It can write a poem that sounds like Shakespeare or make an image that looks real, but it doesn't.
Yeah.
It doesn't get it.
Not at all. It's all just probabilistic mimicry. You ask a standard model to, say, generate a video of water spilling. It does a decent job because it's seen a million videos of spills.
It's memorized the pixels.
Exactly.
Yeah.
It has zero concept of fluid dynamics or gravity. It doesn't know why the water moves that way.
Which is fine for, social media filters. But we're looking at this from an engineering standpoint today. If you're modeling subsurface flow for a geothermal plant, you can't hallucinate a pressure gradient.
No, in engineering, a hallucination is what we call a catastrophic failure.
Right.
And that brings us to the source material for today, coding the laws of nature. We're talking about physics-informed neural networks, PINNs.
Yeah, and the mission for this deep dive is, well, it's pretty straightforward, but the implications are massive. We're actually moving away from just data loss.
They do it at MSc.
The standard stuff, yeah.
Yeah.
And we're introducing physics loss. We are literally embedding differential equations directly into the loss function of the network.
It's probably the biggest shift in scientific machine learning in the last decade. You stop the model from just guessing, and you force it to obey the laws of physics.
So for everyone listening, think of this like a senior engineering sync. We're not going to define what a neural net is. You know that. We want to get into the weeds of the architecture, the specific implementation of Autograd.
Which is the real hero here.
It absolutely is, and how this approach can actually beat traditional solvers in fields like, say, geology.
Let's do it.
So I want to start with the problem statement because it really defines the whole architecture. In standard deep learning, like computer vision, data is cheap, right? You can scrape billions of images.
Yep.
But the source makes this great point that in physical engineering, and they use subsurface geology as the example of data, is incredibly expensive.
It's the whole data-poor, physics-rich mantra. That's what you have to remember. If you're a reservoir engineer modeling groundwater, your data comes from drilling a borehole.
Which costs a fortune.
Millions of dollars. So you might have this reservoir that spans, 10 square kilometers, and you have exactly 3 data points, 3 holes in the ground.
Okay, so if you throw a standard MLP, a multi-layer perceptron, at a grid that big with just 3 points, what happens?
It's a disaster. It fails miserably. A standard neural network is a universal approximator, so it will perfectly memorize those 3 points. Your training loss will go to 0.
Looks great on paper.
Looks great.
Yeah.
But in the space between those holes, the other 99.9% of your domain, the model's output is garbage. It'll oscillate wildly or just flatline. It has absolutely no reason not to.
It's just unconstrained optimization. It's overfitting to the tiny bit of data it has because it has no concept of the signal's structure. It doesn't know that water has to follow Darcy's law.
Precisely. And that's the core distinction. A pure data model thinks water pressure can, essentially teleport from point A to point B if the stats kind of suggest it. But we know, a priori, that the whole system is governed by a partial differential equation, APDE.
So let's get into the solution, the PIN. The big innovation is changing that loss function. We're all used to seeing loss, MSE, prediction, truth.
Standard supervised learning.
Yeah, but that only works if you have the truth to compare against, and here we don't.
Right, so the PIN introduces this composite loss function. It's basically loss total, loss data, plus loss physics.
Okay, so the loss data part is what we know. We force the network to match the measurements at those 3 boreholes. That pins the solution to reality.
It anchors it.
Anchors it. But the loss physics part, that's where the magic happens, right? This is where we use the PDE itself.
Yes. So let's take the example from the source, Darcy's law. In a simple 1D form, it just relates the fluid flow rate to the pressure gradient and the rock permeability.
So you have a differential equation that you know must equal 0 everywhere.
Everywhere in the domain, yes. So here's the workflow. The neural network takes in a coordinate, say 6-axis, and it spits out a prediction for the pressure degree. We don't have a ground truth for Pero at that random point. But what we can do is plug that predicted pair into the differential equation.
We check the math.
We calculate the derivatives of the predicted pressure with respect to location dpdx ASLR. We plug it into Darcy's law, and we see if it all balances out to 0.
And when you start with random weights in the network, it's definitely not going to be 0. It'll be some random number.
Some garbage number, yeah. And that garbage number is what we call the residual.
The residual.
So if the physics says the result should be 0 and your network gives you, say, 5, your physics loss is 25 to 5 squared, the optimizer's job is now to update the weights to drive that residual down to 0.
This leads to something really interesting that I think gets overlooked. For standard deep learning, you need labeled data, input, output.
Always.
But for the physics loss part of a PINN, you don't actually need the label, you just need the input coordinates.
That's the whole collocation point concept.
Yeah.
And it's vital because we don't need ground truth for the physics part. We can just generate a massive virtual data set.
Okay.
We can randomly sample, I don't know, 10,000 points, 6x like that, inside the rock formation where we have never drilled.
So you're basically asking the model, look, I don't know what the pressure is at this random point.
No idea.
But whatever you predict it is, it better satisfy the conservation of mass and Darcy's law.
Exactly. You're flooding the domain with physical constraints. So even though you only have 3 real data points, you've got 10,000 physics points, making sure the curve that connects those holes is physically plausible.
The model isn't just interpolating anymore, it's actually solving the PDE.
It has to.
But, okay, this brings up the implementation nightmare. You mentioned calculating dpdxe buys. To check that residual, we need the derivative of the neural network's output with respect to its input.
Yes. And this is where most people get tripped up. In normal backpropagation, we're always calculating the derivative of the loss with respect to the weights. That's how we learn.
Right.
But here, we need the derivative of the output with respect to the input.
A spatial derivative, the slope of the curve. Now, if we were doing this in a traditional numerical solver, a finite difference method, we just approximate it.
You take $0.6 and 0.6 plus t, subtract them, divide by dollars, which it's fine for simple things, but it introduces truncation error. And it's a real headache to build that grid, the mesh, for a complex 3D geometry.
Or you could try symbolic differentiation, like in Mathematica.
And that just explodes computationally.
Right.
If your neural net has 5 layers with ton activations, the symbolic expression for the derivative is, it's pages long. It's way too slow.
So we land on the secret weapon from the source, Autograd, automatic differentiation.
This is the engine that makes the whole thing go. PyTorch, TensorFlow, they were built for backprop, but the tech underneath Autograd is actually much more general. It just tracks every single operation, addition, multiplication, tan, and applies the chain rule.
And I want to stress this for the engineers listening. We are not talking about a numerical approximation.
No, not at all. This is exact.
Yep.
It computes the derivative to machine precision. When you call torch.autograd.grad, it's giving you the exact analytical slope of the function that the neural network represents at that specific point. No approximation error, no grid.
That's the game changer. That means the PINN is mesh-free.
Right. Think about traditional finite element analysis. You spend 80% of your time just building the mesh, fitting little triangles to the geometry of your part.
And if you mess up the mesh,
your whole simulation crashes. With PIN using Autograd, you just sample random points. X, torch.rand. Done.
So let's walk through the actual Python code from the source, because it's a little weird if you've only ever done classification models. You got your class, PINN, the forward pass looks normal, but the training loop.
The training loop is where it gets spicy. First thing, you have to enable gradient tracking on the input itself. X requires xgrad.
True.
Which we never do in standard ML, right? Inputs are they're just constants.
Correct. But here, you need PyTorch to build the computational graph all the way from X, not just starting at the first weight layer. So you pass X through the model, you get your prediction, U.
And then comes the physics check. You call torch.autograd.ingrad. You pass in outputs, U, inputs, X. And you usually have create a graph true turned on.
And you have to have that create a graph true, because the derivative itself is now part of your loss function. So you need to backpropagate through the derivative calculation to update the weights.
So you're taking the derivative of a derivative. That sounds computationally heavy. It is. It is heavier than a standard forward pass, absolutely. You're basically doubling or tripling the size of your computational graph, especially if you're solving something like the heat equation where you need second-order derivatives, like 2D by 2,2.
Right, because for the heat equation, you need the second special derivative, the Laplacian, and the first-time derivative. So you're calling Autograd twice on the spatial coordinates.
Exactly. And that's the trade-off. PINs are definitely slower to train per epoch than a standard model because of all this calculus. But you need orders of magnitude less data to begin with.
So let's connect this all back to geology. We have this architecture. We have a loss function that punishes any violation of Darcy's law. We have Autograd handling the math perfectly. Why should a senior engineer at an oil company or a geothermal startup care? Why not just stick with NSYS?
Two big reasons. The
Hmm.
first one is inverse problems. This is the killer app.
Explain that.
So traditional simulators, like ANSYS, they're forward solvers. You give them all the rock properties, permeability, porosity, and the boundary conditions, and it tells you how the fluid's going to flow.
Okay.
But in the real world, we usually have the opposite problem.
Mm.
We can measure the flow at a few points, but we don't actually know the rock properties everywhere. We don't know the permeability.
So we're trying to work backward from the sparse data to find the parameters of the system.
Exactly. In a traditional solver, that's an iterative nightmare. You guess a value for Towsers, run the whole simulation, check the error, update your guess, run it all again. It takes forever.
Right.
In a PNN, that parameter tile, the permeability, it's just another trainable variable in your network.
Wait, hold on. That's slick. So you just add tether dollars to the same list of things that the optimizer is allowed to tweak.
That's it. You just tell the optimizer, hey, your job is to minimize the data error and the physics residual, and you're allowed to adjust the weights of the network ND, this physical variable dollars.
Wow.
So in one training run, you solve for the flow field, and you discover the physical properties of the rock at the same time.
That turns a calibration process that could take weeks into an overnight training run.
Pretty much. And the second reason is how it handles sparse, noisy data. Traditional solvers hate noise. A little bit of jitter in your sensor data can completely destabilize a finite element sim.
But neural nets are good at that.
By their very nature, they're good at smoothing out noise. They kind of act as a natural low-pass filter. So the PNN naturally handles the messy reality of field measurements way better than a rigid mathematical grid does.
I do want to push back on one thing, though. This sounds a little too perfect. I know the optimization landscape for these things can be nasty. You're balancing two loss terms, data loss and physics loss, and they might have completely different magnitudes.
You've hit the nail on the head. This is a huge problem. It's often called gradient pathology. The gradient from your physics loss might be like 10 to $5, while the gradient from your data loss is 10 to 1. The optimizer is just going to ignore the physics.
And you end up right back where you started, a model that memorizes the boreholes but violates physics everywhere else.
Exactly what you tried to avoid. So in practice, yeah, implementing this requires some careful dynamic weighting. You have to normalize the gradients so they can compete fairly. There's a lot of engineering in just getting these things to converge. It's not just import pin.
And there's also the spectral bias issue, right? Neural nets are lazy. They struggle to learn high-frequency functions.
They really do. If your groundwater flow has sharp changes or, some kind of shock wave, a standard MLP will just smooth those out way too much. So you have to use things like Fourier feature embeddings to map your inputs to higher frequencies to force the network to pay attention to those sharp details.
See, this is why I love this topic. It's not just add more layers. It's this convergence of classical numerical analysis, the stuff we learned in Fortran 20 years ago, and modern deep learning.
It really is. It stops being data science versus physical modeling.
Yeah.
It becomes one single workflow. You're embedding the differential equation inside the learning process.
So looking ahead, the source says they're starting with Darcy's Law, which is mostly time independent. But part 3 of their series is going to tackle the heat equation.
Time-dependent PDEs. That adds a whole new dimension, literally. Your input is now 6x YT.
And causality becomes a real issue. The future has to depend on the past.
It does, and a standard PNN can struggle with that because it tries to solve the entire space-time cube all at once. So people have developed techniques like causal training, where you force the network to learn time step $2 before it's even allowed to see the data for $2.
Like curriculum learning.
Exactly like that.
Oh.
You're teaching the AI the initial conditions before you ask it to predict the future. It's a very human way of training code, really.
So, to wrap this up, if you're listening and you work in a field where data is sparse, but you know the governing equations, structural mechanics, thermodynamics, geology, this is the toolkit. You don't have to choose between a dumb black box AI and a slow, rigid simulator anymore.
You can have both. You can use Autograd to enforce the laws of nature right inside the neural network.
It's like you're compiling the laws of physics into the weights of the model.
That's a beautiful way to put it.
Well, I think we've unpacked the why and the how. The big takeaway for me is that Autograd is so much more than a tool for backprop. It's a full-on differential engine just waiting for us to use it for physics.
Absolutely. The tools are there.
Yeah.
It's all about framing the problem in the right way.
Well, that's our time. Hopefully this helps you bridge the gap between your old differential equations textbook and your PyTorch scripts. Code hard, stay curious. We'll catch you on the next deep dive.